Welcome to the shop, everyone. Going to talk for a little bit about making precision measurements on a surface table using V-blocks. So this is to get you introduced to making a couple different measurements using a couple different tools, something that we see commonly done with engine overhauls when we're looking at crankshafts, camshafts, things like that. Effectively, we have V-blocks right here that are going to support the crankshaft above the surface so we can rotate it freely and keep it in one spot. I have a straight edge down here, which I've used to make sure that both V-blocks are aligned. If they are not aligned and perpendicular, then it's going to throw off our measurements we get and we can see issues. The measurements that we're looking at with a crankshaft or a camshaft typically are going to be one of three measurements. We're looking at out-of-round measurements on each of the journals. When we talk about journals, we're talking about these places where bearings will rest. These are all considered journals. We take measurements on those in three different places in order to see if there's any out of round, meaning that the journal itself would be kind of egg or oval shaped. We also have a run-out check, which means we're checking to see if the crankshaft is actually bent or bowed in the middle. Typically, the manual is going to provide you a couple different stations to take these measurements from, and we can use that to see if the crankshaft is bowed at all using this dial indicator. The last one we'll see is a wobble check, which is over here on the crankshaft flange, and it's typically to see if the flange has been bent. Most often when this measurement is taken, it's usually in response to some kind of incident. If we have a prop strike, there's a potential for the crankshaft to be bent. We need to check the crankshaft dimensionally to make sure that it is sound, and oftentimes that gets partnered together with some kind of non-destructive inspection. So let's start off with the dial indicator check for run out rather. I have the dial indicator set up. It's a magnetic base. You turn the little switch 45 degrees in order to get it to stick on the metal table. And then we align this onto the journal. Something I want to notice here is we have this oiler hole right there, which is obviously going to cause an issue with our measurement if this little pin runs over it. So we need to be slightly offset in order to get that measurement done accurately. Once I have this brought into the crankshaft and this pin is deflected a little bit, I need to reset my indicator for 0, just like so. We're now pointing at 0. What I'm looking to see is how much this needle deflects, positive or negative, from 0 as I'm measuring through. I have the pin angled this way, so I'm going to rotate the same direction as the pin to alleviate any potential binding on the journal. So as you watch what happens here, I start to rotate the crankshaft. I'm looking for any deflection on this needle right here. Right now I've deflected negative about 1/1000th of an inch, and I hit my cheek on the crankshaft here. It's something to watch out for. So I'm going to make an adjustment. I'm going to move this slightly out of the way. And the beauty about this is I can really recenter wherever I need to. I made sure I'm clear here. We look good. So I'm going to recenter on 0. That's beauty. We can set 0 wherever we need to. Now I can continue measuring again. So here we go. Rotate about negative 1/1000th right now. And we start coming back up towards 0 as we make our revolution to positive 1/1000th. So that gives me a total deflection of 2/1000ths, which if that is within the run-out tolerance for this crankshaft, I'm good to go. The key with this is you usually want to make at least 2 or 3 revolutions to get the same measurement each time to make sure that you haven't gotten a bad reading because it's slightly out of position. As I finish my third measurement, I see the same amount of deflection. Everything looks good. So we're looking at 2/1000ths of an inch. And again, that's calculated because we went negative 1/1000th and positive 1/1000th. Together, we have 2/1000ths of deflection. Next, I want to show you how we make the out-of-round measurements on these journals. To do that, we're going to use our micrometer. So the way that we make this measurement is I'm going to set up in one position. Typically, we want to take a measurement from 3 points and average that across to see what our actual deflection is going to be. Whenever we're using a micrometer on a round object, you have to be very careful to try to make sure we hit right at the widest point, which is usually indicated by the fact that we get just a little bit of a drag of the micrometer in one spot, but not so much that it binds. That feels pretty good right there. I can slide it off easily. I'm going to take my measurement that way. That was one measurement at that orientation. I'm going to move about 30 degrees and take another measurement, like so. A little bit of drag, we look good. I'll write that down after I read it, and then I will take a third measurement in a third place, again, so we can average those out. Just like so, that feels pretty good. A little bit of drag, I'll read that and write it out, and then I can make my average measurement. That average measurement is going to be what our overall diameter is in average. Also, the difference between our highest measurement and our lowest measurement is going to be the total number for out of round, which again is called out in the manual. The last thing I want to show you here is how we do a wobble check on the flange. So I'm actually going to need to move my dial indicator over to the flange of the crankshaft here, and I'm going to set this up so that we are just pressed into the front of the crankshaft flange here, like so. Just like that. So we're pressed into the front of the crankshaft flange. I'm going to actually rotate this just a little bit. There we go. I want to make sure I'm clear of the holes for the propeller bolts, but otherwise it's set good. I can lock this in place. It's not going anywhere. I can reset to 0 on my dial indicator, and again I'm going to rotate in the direction that my pin is pointing here. So we start rotating. There we go. I can already see I'm at about positive 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There you go, all the way back. What I'm seeing here is that this actually, even though it's hard to see, there's quite a bit of wobble on this crankshaft flange, which is probably the reason we wound up with it, because it was rejected for that reason. Something to note is as I'm making this measurement, if it moves back and forth in the V-blocks, then it will throw off my wobble measurement. So I want to make sure that the crankshaft is as far back on the V-blocks without being distorted at all to make sure that we're getting the right measurement. That's the quick run through on how we take measurements on a crankshaft on the surface table using precision instruments. That is what you're going to do for your lab for precision measuring according to the crankshaft you are assigned. Of course, you will need the manual to be able to check the reference points where you'll make these. A final note on this, depending on the type of crankshaft that you're working with, the way that these journals are numbered are going to be different. With a continental crankshaft, we number starting number 1 at the rearmost and move our way forward 1, 2, 3, 4, 5, 6 as we go towards this end of the crankshaft. With Lycoming engines, it's going to be the reverse. We start up front with number 1 and go 2, 3, 4, 5, 6 all the way back. So make sure you know which one you're working on to make sure you're on the right journal when you're making those measurements. Hope you enjoyed. Hope the lab goes easy. I'll be able to answer questions for you when you start.